welcome back. Let's take a look at how to figure out how to tune this query, and let's play around with it a bit. All right, I am now in the file, in the solution file, the O2 solution file that contains suggested solutions and working with it. And the first thing I'm going to do is just take a look at the execution plan. Let's see if we can get the Solution Explorer to go away, though. In the query itself, I'm just going to go ahead and let's run it first for the popular names. I have my actual execution plan button right here turned on now so that I can get a graphic plan showing me how SQL Server has executed the query. I do still I've turned on statistics, time, and IO in this window as well so that I can see, yeah, my execution line, it's in the ballpark of what I was doing before. It's not super dramatically different. It's within the variation I would expect for this. Looking at my execution plan here, I can see that I've got all sorts of interesting stuff going on here. Now, I am using a preview version of SQL Server Management Studio. So if you are using version 17 or before, there may be some things in this execution plan that are different than what you've seen if you're seeing an earlier version. This is preview. It's not fully supported yet. It's a trial one, but I think it's great to get a view of these before they come out, right? We're using this against a test environment, so I think it's quite useful to get a feel for these in test environments before they become readily available for everything. So that's why if you're not running this, some things may look a little different. Like you may notice, hey, look, on this nested loop operator, for example, why does it say 7,742%? It's showing us some more info. It's saying I got 608,000 rows. There's still a hatred of commas in tooltips and everything in Management Studio, so we have to provide our own commas. I expected 7,858 rows, so I got 7,742% of I got more rows than I expected by a lot. So that's valid for that to be greater than 100%. The first, still, when I look at this, I'm like, we're so used to seeing the cost numbers, which are a cost of this operator relative to the entire cost of the plan. This bottom percentage isn't that. It's more based on how much data is flowing through relative to the amount of data the plan was compiled expecting would flow through there. We also, of course, have some information on runtime at that point. Now, looking at this, we know, hey, our total execution time was not 2.6 seconds plus 2.9 seconds plus 1.9 second, right? So in this plan, we are fully in, I don't have column store indexes on this table. This is all row mode. And so this 2.9 here is cumulative, including the children on it to the right. So that's a little bit of an overview of some of the stuff showing in here you may not have been used to seeing. You can figure out a lot of this information by, even if you don't have this version, by hovering over the tooltip. So we were expecting 7,858. We got 608,000. If I hover over this bar, I can see those numbers, this time with a decimal, but still no commas. I can see some of that information is out. If I want to do percentages, I'm going to have to do the math myself, though. So what do we got going on here? How is this happening? Well, our first join that we see back here is a nested loop join, and that join is between the ref.firstname table. Now, I know offhand from having worked with this database that ref.firstname is a unique list of names. It's a relatively small table. So we are doing a clustered index scan of that entire table, but it's a pretty small thing to scan. So, scanning a big table can be a lot, changing that can be a lot more effective than changing a scan on a small table, right? So yeah, that's not ideal, but it's a really small table. And we can't change the indexes, so we may have to live with that. We'll see. Now we've got an index seek down here on the larger first name by birth date table, 2002 to 2017. And, oh, by the way, out of here, we got 3 out of 3 rows out of ref.firstname, which is exactly what we expected. The estimated cost of doing this scan was very low. Now, on this table down here, the larger table, the estimated cost of doing this as compared to the cost in the whole plan was also very low. And we're showing 0.083 seconds. We did a nice seek on this non-clustered index. So we were able to go straight to the rows that we wanted. We did get more rows back than we expected. So that is something that happened. We have just built this index fresh. I just built this index. I created it. And when we create an index, it also creates statistics that go along with the index. And those are created using a full scan of the data. So it looked at all the data when it created those stats, but stats are still estimates. And it can be difficult so we're estimating how many rows are there for 3 different names. It can be tricky to get that right. So it had underestimated that number. So looking at this index seek, I'm now hovering over there and looking at the tooltip. So what happened here? What were we seeking on? We were seeking on the first name ID equals scalar operator, Babby names ref.first name ID as first name ID. We are seeking on the first name ID. We are outputting the fake birth date stamp and the first name by birth date ID. That first name by birth date ID is on the table a unique identifier for every row that is a leading part of the clustering key. So it's figuring out how do I quickly, in the table itself, in the clustered index of the table itself, I have the identifier so that for each of these rows, I can quickly find that if I want. So we're doing a nice efficient seek here and then outputting some extra columns for that. We join together the first name and the related first name ID. So the way the flow goes is, this is a nested loop join. So what happens here is we come in here first and find, hey, what are if we hover over this and look at what's output here, we're saying base the predicate, we're going to look at all the rows and we're going to figure out where the first name equals first name 1 or first name 2 or first name 3. And then we are going to output the first name ID as well as the first name. We then, for every row that comes out of here, we're in a nested loop. So for every row that comes out of here, we're going to go down and we are going to do that index seek. We've got the first name ID and this index leads on first name ID. So we can immediately find the row for that and it gives us the identifier for here's where to find that row in the base table because we don't have an important piece of information yet. We don't have multiple important pieces of information yet. What we've got is the first name, the readable form. We've got the first name ID, the integer, and we've got the birth date stamp, not the birth year. We've got this base column birth date stamp, and then we've got the ID to find the row in the table. We do not have the gender. And we do not have birth year in the form of a year only because it is a computed column. All right, well, we have a compute scalar here. Hey, guess what? This outputs birth year because this compute scalar is the computed column birth year saying, hey, I'll turn that longer detailed birth date stamp into a birth year. So by the time we get up to this nested loop, we do have the birth year, but we still don't have the gender. The gender is not in that index that leads on first name ID. Now we do have a non-clustered index that leads on gender and also has first name ID. So, but do we use that? Well, no, we don't. Even though, this is a fair amount of babies, we actually think that this is only our estimated number of rows. We think this is only about 8,000 babies. Actually, it's like 608,000, right? And that confusion came from down here on a freshly created index that had, my statistics are not out of date. I just created this. It looked at all the data. It's simply, statistics are very small and lightweight. The histogram in there that kind of has data like this, it's going to have a couple hundred steps at most. So how descriptive can it be of every single name in the database? It's really hard. Plus, we're doing this join between first name ID and first name on 2 tables, right? Our predicate is on first name, and then we're joining to another table. So this is actually really, really hard to make this estimate perfect. It is pretty reasonable that this estimate could be quite off. just, and the nature of normalized databases and needing to do these joins, it's not uncommon that this might be a problem. So just updating the statistics, that's going to be a hard approach for this, but it is something for us to keep in mind that we need to handle. So based on the fact that it's like, oh, there's only 8,000 rows. It's like, oh, it won't be that painful to just go do a key lookup. Now, based on having looked at this tooltip before, we can look at it again. But based on having looked at this before, what it's outputting here is the gender, right? Because we need to have the gender to do our group by of, for this first name, gender, and birth year, I need to count them up and then rank them. So we need the gender. So it's saying, oh, it's just 8,000. I'll just go do this key lookup. We thought, it would just be this much work. Turns out it was more than 600,000 times. SQL Server, even with the low estimate, right, we did think that this wasn't going to be too bad. Now, this cost here, let's hover over here. And now we're looking at, the estimates in the tooltip, right? So this is saying that exactly what we're seeing in that summary thing. It's a little weird because when you look at estimated rows, it's 1. That's 1 per trip. The estimated number of executions is, I'm going to have to go do this lookup 7,857 times. On each time I expect to get 1, right? So we do have, kind of the same information there, but sometimes it's phrased in a slightly different way in more detail there. And if we want to look at the output list, we can see, in fact, it is outputting gender. So this is, we can see from the time here. Yeah, this is taking up one point, at this point where we finish executing this, it does look like this is taking up a lot of time, for sure, right? So, but of course, this is, a cumulative thing, but our timings here are lower, right? This is the point at where, oh yeah, our time is really jumping up when we get to this part of this nested loop here, right? By the time it completes this, we're at 2.634 seconds. The rest of the query doesn't seem to add too much time on it. We're going from 2.634 to 2.9 and up from there, right? So it seems like, yeah, this is where we want to troubleshoot here. Well, let's take a look at just different things we could do. So is it possible, and instead of being solution one, this is really testing, right? We're doing some testing here because this version of the stored procedure, let's just call this test 1. That's much more correct. And we'll just call it testing because I've got a couple tests in here. So in a situation like this, one of the things I would be curious about is, okay, so what I'm doing here is I'm grouping by gender, right? In my original query, if I look at our original query, we have the predicates that we're giving it are just on first name. We are grouping by gender, but I'm not, giving it predicates for gender because I want to group by all of the genders that I have. I happen to know that, based on that check constraint, I know that we only have 2 values in this table for gender. So I'm going to change the results while this is just a test. And in the real world, I certainly wouldn't test this in production because what I'm going to do here is say, okay, well, I want to know how my query plan changes if I say not only where the first name is in these values, but where the gender equals M. So if I give it a specific value, I am still grouping by gender. I am still ranking by gender below. The only thing I've said now is I'm going to give you a predicate on gender and see how the query plan changes just as an action to help kind of inform me about what you might do and how that might perform. So this is a step that when playing around with and tuning queries, sometimes I will, in a test version, add in a predicate that I don't intend to leave in there simply for the purpose of examining what changes in the plan and how does performance change, because that information can lead me to different performance tuning tactics that maybe take a little longer to write rather than simply, adding in this predicate there. Let's see how that runs. I am expecting, of course, not to see any results for the gender equals F here. So let's go ahead and let's run it one at a time. We'll run it first for John, Jacob, and Mary, and that didn't take too long. Now, admittedly, I am looking at fewer rows, right? Not only does my predicate, change the result, it also narrows down the results that we're ranking. So it would make sense that it would be faster. Sure enough, we're seeing gender equals M. Our execution time, these are the slower names. Hey, our execution time ain't looking bad. 422 milliseconds. That's not so bad. That is, less than 50%. And we are looking at that, and hey, SQL Server's asking for an index now. There we go. Tooltip fell. SQL Server is now suddenly saying, hey, an index on ref.firstname would be great. Well, you could ask, it would have been great in the last query too, but it's changes in query plans can result in SQL Server asking for things it didn't ask for before. It is now suggesting that index, but we're not doing index changes, so thanks SQL Server. So our query plan does look quite different here, huh? Look at this. So what we're doing now, we're still doing, this is the same. We were before our driver table at the top right. I like to call it the driver table. Sure enough, we are still doing a clustered index scan of ref.firstname, and we still have, let's see if I can get the tooltip visible on the screen and zoom at the same time. We still have the same predicates on there, right? We want first name 3 or first name 2 or first name 1, and we're outputting first name ID and first name, right? Nothing revolutionary there. We're going into a nested loop, but this time we are seeking on a different index. We selected a different index. This time we decided to seek on the index that leads on gender and first name ID. Well, what are we seeking on? Well, now we have a different option because we have this index leads on gender. Before, we were saying we want all the genders. Yeah, I mean, there's only 2 of them actually in the table. But this time, the fact that we said we only want the male ones said, oh, I can do a seek on that because in my index for the male babies, I have this index, everything's sorted by gender and then everything's sorted by first name ID. So a nested index or a nested loop makes sense here. What I'm going to do is I'm going to do this scan here and find for all of the babies based on that first name. What are the first name IDs? So for all the first name IDs, I'm going to go out here to the nested loop, and then I'm going to go down here, and I'm going to seek on, I know the gender is M. You have that as a predicate, so I'm going to seek to the male babies, and then the second ordering column is first name ID, so I can seek straight to them. That's fantastic. So the fact that we have restricted the data set let it seek for this. Now, could it have done this in the first query? Well, if SQL Server had known, if the optimizer had realized, if it had realized, hey, you want to do this, and there's only male babies, and there's only 2 values in here, I could seek once, I could assume, hey, I'm going to seek for all of these first name IDs with M. I'm going to seek for all of these first name IDs with F. Yes, in theory, it could have figured that out, but it doesn't, it's not smart enough to put together, in this case, that specific information from the constraint with that plan. It didn't work. It didn't make that choice, right? But this time, the addition of that gender equals M, it was like, oh yeah, I can seek on that, right? And it does so. Even though our estimate here was higher than expected, I mean, look, by the time we're done with this nested loop, we're only 128 seconds in, right? Yes, our estimates are still not perfect. It's going to be, with the way that we are putting the predicate on the name and then we're joining on first name ID, that's going to be a toughie, but sometimes it's fine if your estimates are off. This is nice and fast, and the rest of the query doesn't take very long as well. So that does speed it up. Now, we don't want just the male babies, so we're not done. But this is giving us interesting information towards our rewrite. Running it for the less popular names now, the Kendras who have a tie are female, so they're not in this list, right? But this completes, and I'm getting values I expect, and the query is nice and super fast for these less popular names as well. We haven't hit a weird plan and slowed it down for them. All right, so if it seeks given males, what if I try this? Let's go ahead and say I'm going to go ahead and alter the procedure, and again, this time, the changes are only in this block. I'm still saying I want, first name 1, first name 2, first name 3. I am now saying, though, where gender is in M or F. Now, I happen to know those are the only values in the table. I even have a check constraint that proves it, but let's see, what query plan do we get after making this change, and how does it perform? kind of a bummer to hard code those values, of course. Now, this isn't a perfect solution, right? Because today, maybe I have that check constraint and maybe those are the only values that come. But what if tomorrow the government starts accepting different values and sending them in my data set? I might want those to automatically appear in this report. I am now locking I'm now saying, oh, if I want to show more values than this in my report, I'm going to have to execute a code change. That is a limitation of this approach. All the times when we rewrite queries, we do have to think about side effects like that of, in the future, if my data changes, is this still going to be appropriate, right? So that's definitely something to think about here. But what does it do? Running this first for John, Jacob, and Mary. And we're just testing the plans that compile for these values. Sure enough, I do now have multiple genders in my data set again. And if I look at my speed, well, CPU time over 3 seconds, elapsed time over 3 seconds. Let's look at the plan. How did we do here? Oh, we are back to, hey, let's do an index seek on the index that's just on first name ID. Let's get the gender out of there. And then it seems like a great idea to do this key lookup. It'll only be 7,858 rows, but and we're spending a lot of time here. So when we had just one predicate in there, we got a plan that was nice and fast. But if we just said, gender in MRF, we didn't get that plan. Now things are still fast for Kendra, Mr., and Stormy, right? We're still at 156. Let's look at what plan we get compiling for them, though. We're still getting that same plan. And this plan with the key lookup here, this plan, if we don't actually have many rows flowing through, right? This time it was only 20,000 rows. Yeah, that's more than we estimated, but right, it's still quite fast, right? So this plan works. If there's not a lot of rows to do a key lookup, it's quite speedy. The more rows end up in that key lookup, the slower and slower we get. Well, we might be tempted to make it seek. So let's go ahead and try this change here. What have we done here? We now have in this section here, we've added a little extra hint. So this right here is the same as last time, where gender in MRF, but I've tried to make it fit. I've said when you're querying the first name by birth date, 2002 to 2017 table, I really want you to do a seek. I really want you to do a seek when you're querying that table. And I put that hint in the my count CTE because that's the CTE where I access that table. Well, what do you think of that SQL Server? There's definitely pros and cons of using these hints. Sometimes if I use a hint and SQL Server can't do it, the query will simply fail. Well, the query isn't failing. The good news is my hint hasn't made the query fail due to the fact that it cannot seek, right? I did get both result sets back. The Kendra result set, we've got the tie like we're expecting. Looking at our execution times, that first query, still around 3 seconds. 3 seconds. Yeah. I mean, the second one's still pretty fast, but yeah, we didn't get what we wanted here. We do have a seek that we are doing a seek on the index on first name ID. We, in addition, are doing a key lookup. So I try these hints as a last resort, and the fact that a seek is good for me now, it may not be good for me later. So yeah, we are always manipulating things, but it's not just as easy as putting a forced seek hint on it here. So let's try something else. Well, I know that when I put the predicate on for gender equals M, I know that was fast. And I know that I can make my query more complicated. So let's try that. We are going to do separate CTEs for each gender. I'm not saying this one is pretty. I'm just saying let's see how it performs. So this sample is longer because what we're doing in here, we are having tons of fun. We now have a my count CTE for the males, right? So I'm saying, okay, with my count M, I am now in this set. I'm going to say I want to look at all of the gender equals M's where the first name ID is in that set. And I am going to group them. I am then going to take the output of this, and then I'm going to rank them in year rank M, which looks at year rank M is right here. It looks at my count M and does the rank. So this is just like what we were doing before. I've just put a predicate in the first CTE and said males only. Then we now have, I've added more CTEs. I have added my count F and year rank F. So here in my count F, I have added an additional CTE. It doesn't have to query the CTE before. This one says, no, I am in this query, I am querying first name by birth date 2002 to 2017. And, I want the rows that have first names that were passed in for gender equals F. So I'm essentially separating my processing for males and females so that I can put this predicate into my query, and I am finding the girl babies with the first names and ranking them, and I'm finding the boy babies with those names and ranking them separately, and then at the end of the query, we will put them back together. Because here I am now I'm going to query the ranked male babies, and I'm going to union all that with the ranked female babies. For both of them, I only want the ones ranked number 1. So this is definitely not a pretty query. One could argue it never started out being very pretty, but it's getting nastier and nastier in terms of like someone looking at this now and having to manage it. It's going to be like, oh, what? What is this? My goodness, I hope you write comments in your code. But, the challenge was not to make the query beautiful. The challenge was to make the query fast. So, okay, let's go ahead and run this for John, Jacob, and Mary. And I have execution plans on, and this did not take 3 seconds. This did not take 2 seconds. This took 437 milliseconds of CPU time with a little more elapsed time. And very, very interesting, if we look at our total logical reads here, 1,920 logical reads with a scan count 6. We've got some parallelism. Let's confirm that in our plan. It is now asking for, when it asks for that index, it means it's fast. So now if we look at our query, here's that union all. I'm saying, okay, I'm going to just query the male babies and query the female babies, and then I'm going to put them together. We've got a concatenation in there, right? That's not taken a lot of time there to do the concatenation because we can look for each branch that their times are actually the top branch here is the one that's time is mostly close to that one. And if we scroll on over here, we can see that for each branch, we have the same plan shape. And these branches are able to run simultaneously and then concatenate. So we still have a complex query, but each of these doesn't have that key lookup pattern. Each of these is saying, hey, I am going to scan ref.first name, and I am scanning ref.first name twice. That is true, but that table's really small. So scanning it twice, 0.017 seconds, right? Not a big deal. And then for the names, the first name IDs that come out, there are only 3. I am now going to go down and seek. And since I know, let's see, this top one, if we look at the seek predicates, it's seeking here for the male babies and that first name ID. Right? It can go straight to those rows. It can get because that index is on gender and then first name ID, it knows the gender, it knows the first name ID out of there, and it can go on and have a lot of fun. By which I mean be fast. It probably doesn't actually enjoy it, right? So this is nice and fast. Is this limiting in the future? Yeah. I mean, if I add additional values, I'm going to have to add 2 additional CTEs if I have extra genders. I don't love that. But sometimes in the real world, sometimes we do have patterns that aren't pretty that we use because they're fast. Now, ideally, we come up with code that's easy to manage and fast. That's still a goal. But sometimes in the real world, we do end up with code that will have to be modified if the data changes in an important way. If we do have that, those constraints are really important to help make sure that the data doesn't change in a way we aren't expecting, right? Because we want to know if we need to change the code. In our results here, I just ran this for the less popular names, the more unique names. And we are still, getting our tie. We're still using the same rank, and the query is still fast for that. We're at 47 milliseconds and 131 milliseconds. Well, what about a different way? Instead of doing that CTE approach, we could use something called a table value constructor, or we could use something, similar. Essentially, the question is, what if instead of saying gender equals M or gender equals F as a predicate like that, what if instead I have a table that lists my allowed genders? Now, I could put a reference table in my database that lists the allowed genders, and I could pull this from a real table, right? That might be useful. In this case, instead of creating a table, I am simply writing a query that creates a little table where one row equals M and one row equals F. This table value constructor, I am saying, here's the values I want you to represent as a table. Alias this table as V. So my fake table is named V, and it only has one column in it. That column is named G. That allows me to do things like join on it. So I'm going to go ahead and put that in my query. One way I can do that is to cross-apply in the query. So let's take a look. I don't have any for secants in here anymore. So now, instead of adding in a predicate where gender equals M, I'm saying, okay, here's my main big table I'm pulling from. I'm joining to first name. I am now cross-applying to my table named V with G. And I'm saying where the gender equals one of the values in the G column. I've got two rows. One is M, one is F. And then same thing as before with the first name. So I am using a constructor to construct a fake table. This could also be a real table that we use as well. How does it perform if we change it this way? Well, look at that. Good news. This isn't bad. I'm at 438 milliseconds of CPU time and 521 milliseconds of elapsed time. My logical reads is only 1,920. Well, what does my execution plan look like? We don't have that same, I'm not, doing a union all in here. I don't have that same concatenation plan. Instead, I am getting a plan where we are, in fact, have a different shape plan. That is, we are only scanning ref.firstname once, and we are doing an index seek let's take a look at this. This is the index on gender and then first name ID, and it is looking at the things that it's finding in that table value constructor that it's finding. So scalar operator, union 1004, scalar operator, that's first name ID equals that value, right? So we are seeking on the gender, which we've got a comma in here. I'm like, oh, this is one of those things. So it's let's resume so that I love looking at tooltips. No matter how often I look at them, it's always an adventure. So our seek keys it's a combo key, right? Gender, comma, first name ID, and then we have the equals the scalar operator union 1004. That's what we're getting from the table value constructor. That's the gender, and then the first name ID that we're pulling from ref.firstname. There we go. So it's a composite seek on two combo values, right? And this is great. This is what we want. Now, if you're looking at this plan and you're like, what is that constant scan? That is the table value constructor there, right? Because I am saying I want to create this fake table with M and F in it, and that is how that is represented in the plan. So creating that table value constructor, I actually like it from a readability perspective, right? Because I can kind of see, oh, the values that I'm allowing are this. I'm still absolutely hard coding the values. That is still absolutely limiting in terms of data changing, but I actually think it's much more readable than adding extra CTEs on. Personally, I still might want to put notes on that. So let's run it for the less frequent names, and those names are still fast. right? So, that's parse and compile time. Our execution time is 47 milliseconds. We could write this in a different way. I did a cross apply there. We don't have to use a cross apply with this particular example. This example just says we could join to the table value constructor, right? In terms of this table value constructor, which is producing a fake table, I could also join to use the table value constructor, name the table X on gender equals the column G in the table X. So that is another syntax that can work. With any syntax change, I want to take a look at the results and execution plans, of course. And this is still nice and fast for those popular names. 469 milliseconds, 516 milliseconds, and I've still got that nice plan with the index seek on the index leading on gender and first name ID there. For my more unique names, also still fast, and when I compile it for that, I am also getting that same nice plan. So this is the, different ways that I went when tuning this. There's a lot of stuff in this query, and I fully expect that folks out there are going to come up with alternatives. So I'd love to hear about the different approaches that you took to tuning this and different things that this made you think of in terms of query writing. That's what it's all about, these exercises, is giving you examples that let you try out lots of different things and, maybe get a little frustrated sometimes when you're like, SQL Server, why don't you do that? But also, just build that flexibility of thinking of different ways to test and tune procedures. Thank you for joining me for this SQL challenge, and there will be more coming up soon, so hope to see you in the near future. I'm Kendra Little from SQL Workbooks. Bye, folks.